Okay, so this video is going to be a quick review of the day 2 of the past paper program. I know I haven't made any videos for a while, so what I'm going to do is just do a review of each of the papers that I put up there. That's 9 of them, and then leave it up to you to let me know if there's any particular questions that you want me to do a specific video about. Just send me an email, and I can do those over the next couple of days. Of course, the exam's not too far away now. So yeah, this is day 2. And let's just go quickly through each of these questions from a kind of a strategic point of view. How would you approach them? Cool, so for question 1 here, we've got a percentage of houses that have solar heating, and we've got 19 houses chosen at random. And then you want to find the probability that's fewer than 4 have solar heating. So that to me straight away stands out that it's a binomial distribution question, where n is 19, that's the fixed number of trials, which is 19 houses, and p is 0.12. And then the thing here is just that it's fewer than 4 houses. So that means it's 0 houses, 1 house, 2 houses, or 3 houses. So you do the probabilities of each of those separately using the binomial distribution formula on your formula sheet, and then add those up. Cool, so for part 2, you've got these 3 different year groups, and you're selecting members to make groups, okay? So this is going to be a combinations question, and you want at least 1 member from each year group. So what you're going to do is do a partitioning approach. So make a list of all the ways that you could select 5 members that have at least 1 from each year group. Make sure within each option that you multiply the combinations, selecting from the different year groups, and then add up those ones to get the overall total. For question 3, looking at this tennis match, and they're doing the first person to win 2 sets wins the match. You've got the probability of Roger winning the first set, and then after that what happens. So this to me looks like it's a probability tree, because you've got things happening in a particular order and probabilities of whether they win or not, so you can kind of set out each stage of the tree is going to be a different match. And then you're going to have to go through and here find the probability there's a winner after exactly 2 sets. So look at what happens after those sets and find out how many of those, add up the ones where it does come out to be a winner. And this one here for part 2 is a conditional probability. So it says find the probability that Andy wins the match given that there's a winner after exactly 2 sets. So you use your answer from part 1 as the denominator of your probability fraction, and on the numerator will be the probability that it's Andy and there's a winner after 2 matches. So basically he wins in 2 matches is your top of your probability fraction for that one. For question 4, you've got coin A and coin B and different probabilities of getting a heads. And then here, coin A being thrown twice and coin B being thrown once. And you have to show the probability of getting exactly 1 head and 2 tails is 13 over 36. So again, looking at that, I probably would go for, you could draw a probability tree. I suppose the thing here is that the events are independent. So you could just sort of list out the ways of getting 1 head and 2 tails yourself. Then multiply coin A twice and coin B once with your outcomes, with your probabilities to work out those for each of the ways you've listed, and then add them up. You could do it that way. Cool, then do a distribution table. So the only thing you have to remember is a probability distribution table is if you're doing it, throwing your these coins here, you've got an option of anything from 0 heads to 3 heads, right? So your probability distribution table would have 0, 1, 2, and 3 across the top, and then the second row would have a probability for each of those outcomes along the bottom. Then you'll use your probability distribution table from part 2 to work out the expected number of heads by multiplying each outcome by its probability as you go across the table, and then summing up all of that to get the expected value. Now on to question 5, which is making numbers out of digits, and you should be used to this by now as being a permutation question. And the key thing here is you've got to watch out for whether they want you to use all the digits or not. So it says here sum or all, and this is the stem of the question. So anything that's in the stem of the question you can use for part 1, part 2, and part 3. So for part 1 it says all the 7 digits are used, which is cool with that 7-digit number. The odd digits are all grouped together and no digits are repeated. So that means, if they didn't put this condition in here for yourself, given that all these numbers are different, okay, they are all different, then initially it would be 7 factorial, right? 7 times 6 times 5 times 4. Here they want the odd digits to be together, so you're going to group the odd digits together, which was 1, 3, 5, 7, and 9. So put those 4 together, which means you're only arranging that group of odd numbers plus the 4 and the 8. So it's only 3 groups that you're arranging. But then within that group of odd digits, you can arrange that 4 factorial times. So it's going to be 3 factorial times 4 factorial. For part 2, you're looking at even numbers. Again, no digits are repeated, which is great. That makes it a bit easier. And for it to be an even number, that means it's got to end in either a 4 or an 8. So what you're going to do is go through the different scenarios. Either scenarios where it ends in a 4 and starts in a 3, or the scenario where it ends in an 8 and starts in a 3 or a 4. Okay, and then if you place those values and then arrange the digits with the spaces that are left over, so fix the first and the last positions and then look at the arrangements within the second and the third position. You'll be able to do that one there, which will be fine. And then for part 3, multiples of 5 which are less than 1,000. And the thing about this one here is if you go back to here, it's just reminding you that you're not necessarily using all the digits, but also if it's less than 1,000, that includes single-digit numbers, double-digit numbers, and triple-digit numbers. Okay, so basically your ones, your tens, and your hundreds. So you got to watch out for that. You've also got, so multiples of 5 are fine because that means it ends in a 5. So you've got that, but also digits can be repeated now. Okay, so you can choose, for example, 5 twice and have 55, and that would be counted. So again, if you just take a systematic approach and go through and think of all the ways you can get multiples of 5, then multiply each of the kind of ways that you've got that within each one, and then add them up, you'll be fine. For question 6, you've got time, which is a continuous variable here, and you've got this cumulative frequency here. So 57 athletes here. And this means anything up to but not including 10 seconds was nobody, anything up to but not including 10.5 seconds was 4 people, and so forth. So this is pretty straightforward. How many ran a time between 10.5 and 11? So that's between here and here. So it's gone from 4 to 10, so that's 6 more people. So good. Part 2, histogram. So if you're going to do a histogram, what do you have to watch out for? A couple of things, remember. So you've got to make sure that you do an axis across, the x-axis is in terms of numbers, not in groups. Okay, so just do a scale from here, a scale from 0 up to 13.5. That's fine. And here you would take each value how it is. Okay, so your first group would go from 0 to 10, and then 10 to 10.5, and so forth. Okay, and then the other thing you have to worry about with your histogram is how you do the heights of each of those bars, and that's you're going to use frequency density for that to make sure that you take into account how wide each group is, so visually it makes sense. So just be careful with that. For part 3, working out the mean and the variance. So that's when they want the variance, which means the squared differences between the values and the mean. So it's really similar to for our normal question asks for mean and standard deviation. So all you have to do here is just not do the square root right at the end of everything you've worked out. But you guys are pretty good with that. So for this case here, because it's grouped, you'd be taking the midpoint of each group as your x value, and then using the formula to work out the mean and standard deviation. Okay, and then question 7, which we put into one of our tests or the exam or somewhere, we've used it before anyway. So you probably are familiar with this one here. So it's a normal distribution question. They tell you the mean but don't tell you the standard deviation, but they do tell you that 80% of the days he spends more than 1.35 on his homework. So what you're going to have to do is draw yourself a graph of that. And you'll realise, for example, here, if it's 80%, then it's something like that. And so in which case this z-score here is a negative z-score because it's below the mean, but you're going to have to look up 80% that way on the graph, on the middle of the normal distribution table, find your z-score and then make sure you make it negative. And then set up a little equation and rearrange it to find out what the value of the standard deviation is for part 1. Then for part 2, you're just going to have to use a normal distribution calculation to work out less than 2 hours, now that you have the standard deviation from part 1. And then part 3, yay, 6 marks, is a normal approximation to a binomial distribution. And the clue is it tells you to use an approximation, which is nice. So you're going to use n times p to work out the mean, and n times p times q square root to work out the standard deviation. And then make sure you use a continuity correction, because they want to be between 163 and 173 inclusive, which means you're going to have to use 162.5 and 173.5 as your calculations.